Nothing in the cosmos can escape a black hole. Once light crosses the event horizon, it is trapped forever. But modern physics has uncovered a fatal exception to this rule. These ultimate cosmic traps actually have a lifespan. In 1974, Stephen Hawking demonstrated that black holes slowly leak energy. Over billions of years, this process, Hawking radiation, causes them to shrink and evaporate. If a black hole can completely evaporate into nothing, it creates a fatal mathematical flaw in our understanding of the universe. Quantum mechanics dictates that information about the physical state of matter can never be deleted. Yet, as a black hole evaporates, every detail about the stars and planets it swallowed appears to be erased permanently. This discrepancy becomes critical at the very end of the black hole's life. As it bleeds away its mass, it eventually shrinks down to a speck, weighing roughly 20 micrograms, known as the Planck mass. At this microscopic limit, the evaporation stops. So, where did all that devoured information go? To resolve this contradiction, physicists realized they had to step away from quantum mechanics and revisit the equations Albert Einstein published decades earlier. This is a Penrose diagram. Physicists use this model to map the entire lifespan of a black hole, tracking its formation from a collapsing star straight through to the unavoidable singularity in its future. Mathematical equations frequently produce two solutions, much like a cone has both an upward and a downward point. When we expand this mathematical model, a second inverted half emerges. General relativity perfectly describes this bottom region as well. But in this mirror image structure, the flow of space and time prevent anything from entering. Instead of a singularity in its future, this object has a singularity in its past. It acts as a cosmic geyser, ejecting light and matter outward into space. The mathematics firmly support the existence of these white holes. But for an object like this to actually form in our universe, there has to be a physical mechanism to trigger it. That trigger might be found in a theory called loop quantum gravity, which suggests space is not a continuous empty void. Instead, it proposes that the fabric of the universe is woven from distinct, indivisible loops. Because space has this minimum pixel size, matter can only be compressed so far. A collapsing black hole cannot shrink into a point of zero volume. Once the collapsing mass hits this absolute microscopic limit, it can no longer compress, causing a violent outward physical rebound. Physicists call this rebound quantum tunneling. In a fraction of a second, the dying black hole turns inside out, transitioning into a white hole and ejecting all of its trapped information back into the cosmos. This solves the paradox. Black holes do not destroy the matter they consume. They merely store it during the first half of a life cycle that inevitably ends in a white hole's eruption. If a microscopic singularity can compress and then bounce outward as a white hole, we have to consider what happens when we apply that exact same mechanism to the largest scale imaginable. According to the Standard Model of Cosmology, 13.8 billion years ago, all matter and energy was compressed into an infinitely hot, dense singularity before rapidly expanding to form the universe. Look at these two models side by side. The physical expansion of the Big Bang perfectly aligns with the mathematical definition of a stationary, uncharged white hole. The mechanics are identical. The violent event that created our universe operates exactly like the white holes predicted by Einstein's equations. Tracing this logic backward presents a jarring physical reality. If our expanding universe is effectively a white hole, it had to originate from a quantum bounce. That means before our time began, a completely different, older universe must have contracted, collapsed into an unfathomably massive black hole, hit the quantum limit of space, and rebounded. Space continuously cycles through periods of extreme contraction and expansion, where one universe's death directly fuels another's explosive birth. We have spent decades searching the distant cosmos for evidence of white holes, but the data suggests we shouldn't be looking out into the void. We are already living inside one.